Hello, it's day 23 and we've got another routing problem. We've got a maze like this. In fact, I'll show you over here. We've got a maze like this, and our job is to find the longest possible trail with a few constraints. If you're on a slope, that is one of these phi or characters, you've got to go in the direction of that slope, in the direction of the arrow. You can't step on the same cell twice either. So you've got to find the longest possible trail while following the rule of going down the slopes, that is in the direction of the arrows, and not stepping on the same cell twice. So when I was first thinking about this, I think we can still do A star, which is basically uh, Dijkstra, is that how you pronounce it? Dijkstra, but with negative cost for steps. I think that will work. I did a bit of research and I think it will work. Uh, So that solves the first one. You can then solve number two by controlling the neighbors that you provide for each cell. And I think you can anyway. Yeah, yeah. No matter what happens, each cell will have the same neighbor, I believe. Yeah, with this exception. So I first thought you could just keep a set of the cells you visited and then not visit anymore, not provide any more neighbors that are in that set. You can't actually do that, and here's why. So let's say that we have this path. So the way this algorithm works, the A star or Dijkstra algorithm, is by exploring different paths through the through the graph or the maze or whatever it is you're looking at. And so here's an example of a path that we could explore and find um, meets the goal. Now, this is all okay, but once we've hit this one, we're going to want to backtrack and see if we can find a um, a shorter one potentially. I think I may end up fooling myself with this algorithm a little bit, but anyway, you'll get the idea when I show you it. So let's say we want to explore this one. Pay attention to this area here, which I'll circle. Pay attention to this area here. So this area here has been visited already. Now, if we want to backtrack and explore a different route, maybe a longer route, once we hit this cell, we won't be able to visit it anymore if we've just strictly, if we just sort of simply kept a list of the cells we visited. Because if we explore another route to it, because you can see these routes kind of, they diverge around here. So in theory, we could end up here and decide we want to explore both paths and which one takes us longer. Now, if we explore this one first and then hit this cell, it will be excluded from, well, it will be in the visited set, and so it'll be excluded from any cells we can visit again. And so when we try out the green path, which to me appears to be a bit longer, but I don't actually know for sure, then we'll stop here because we can't visit this cell again. So that poses a slight conundrum, which I've solved by. So first thing I thought of, well, let's keep a frozen set of all the visited cells in essentially the position, so the state that we're looking at as we move around the graph. That would get quite large. Each cell would essentially have a list of each position would have a list of all of the positions it's visited so far, and that could become expensive. It may not, it may still be manageable, but it gave me a sort of bad feeling. So I worked out that there's a way of reducing that by only keeping track of what I've called the inroad cells. Move this back over here, we can look at those. So the inroad cells are the cells that have two or more, I think exactly two basically, ways into them. If they've got two ways into them, we need to keep track that we've visited those cells. That's the only way that we can possibly end up going back over our own footwork. I mean, this is my assumption. This is my belief anyway. Let me just double check that. Is there any way that we could? No, I think we will have to go to a cell that has more than one way into it in order to visit a cell twice. So if we only keep track of the inroad cells that we visited, and you can see there are only 4 on this graph, on this maze here, then we're going to be okay. We just need to not visit those. So that's all right. So not this way, this way. Again, I may prove to be wrong about all of this, but you'll be able to tell possibly from the length of the part 1 whether I am. I've created a bit of a kind of class plan. So I've got a state. I'm going to keep track of this cursor, which is going to be the thing which tracks our position and the inroads that we've visited so far. Cell, which I'm going to do something slightly different with. I'm going to, rather than having all the logic around exits and entry points spread out throughout the program, I'm going to try and keep it inside cell and see how that feels. And I'm going to steal a bunch of code from step 17 as well, because I can reuse a bunch of that stuff, which is quite fiddly. And I also created some other mazes just for testing purposes. My feeling is my verification process currently could do with some smaller inputs crafted by me. So I'm going to try out that approach as well today. I've got my plan as well, so I'm pretty much good to go. I am going to switch to the code now. Move that up here, around here, move myself around. Get rid of this. No, no, no. Okay. And let's switch to the code. Why is this so wide? Okay, great, great, great. All right, and let's go. Okay, so that's our vec. Now we want a. We may need to copy some of the rest of this stuff as well. Don't need this. Don't need this. We need this. Okay. Let's go with cell. Great. Okay. Okay. So this is going to be I think I have this code somewhere. Oh well. Just copy this and cut it down. We don't want this. We don't want the diagonals. Okay, so this, yeah, it's going to be true. Let's get this. All right, so we've got up, right, down, right. So this is up, this is down, this is right, and this is left. Okay, great. That's good. So now we want to check if this is a slope, we in fact only want one, which is the one that goes right. Now, if we have this slope, we want the one that goes left. If we've got this slope, we want the one that goes up. And then if we've got this slope, we want the one that goes down. Okay, great. So now it's if type is the dot, then we can have this. Let's copy in. Where's our thing? This is left. This is up. And this is down. Oops. Let's go with kind because type is clearly not right. Okay, and now just for completeness, let's have a block here which should return an empty set. Okay, great. So that's the ways we can exit. Now for entries, what do we have? For the dot, it's you can also enter from anywhere. For any of the other slopes, it's the same. And I think it's essentially for the block. Yeah, this is the logic. Nope. Probably could have done that a bit faster. All right. Okay, at least there's no mistakes there, I hope. Great. Okay, cursor then. Now, this one was our cart before. I think basically we just delegate this to, yeah, in fact, I don't think that's useful to have. We can add it later though. And this is going to be inroads. It's really inroads visited. Don't need the order on it. Okay. Now we can go with state. And for this, I'm going to start parsing the line. Yeah, and what do we have here? Okay, that's good. All right. Let's try this again with Okay, great. Okay, now we've got um, let's go with next we can go with is inroad. So the logic for this is we get the entries for the cell, and then we filter that based on what is actually in those. So if all entries, no, if cell, no, it's actually a vec. If so actually we probably don't need this strictly because there's a border around the cells, but let's check it anyway. We have this on a new line, and so we're not off screen, and the cells around us. Yeah, okay. And self cells vec entries. Yeah, okay. Okay, so in this case, we've got one cell which is an inroad. So let's check that. Actually, let's first check is inroad for let's go x is 1, y is 0. Okay. Now what about when y is 1? Okay, good. 2, great. Okay. 2, 3, 4, 2, 3, 4, 5, 6, 7. Should fail. Okay. Is anything working at all? So actually, this is not working. What about this? This? Okay. So let's look at this with just this one. Okay, so it's a dot. Hmm, that's better. Okay, so we've got the right cell. We've got the entries, which includes the y up from this 7.4, which should be 7.5, which it is. No, wait. Yeah, we got the 7.5, yeah, and we got the, yeah, okay. So it's not off screen. Okay, they're all on screen. That's good. And then we're getting this the cell at that vec. Ah, exits. That's it. Okay, so that one's understandable. What about this? Okay, so that should be making it in there. Seven five is the one down. So that's the cell we're printing for. And oh, and actually, we're going to need to find a way to avoid us backtracking on ourselves as well. Anyway, um, okay. What's 7.5? Let's look at 7.3 because this one really should be in there. And the exits for 7.3 are just empty for some reason. Oh, 7.4, which should be the here. That should be right. Couldn't be a precedence, could it? No. Oh, ugh, that was a waste of time. Okay, so 1, 2. Yeah, so it does have multiple inroads. No, 1, 2 doesn't actually. What is 1, 2? Yeah, it's that one. So it does really have multiple inroads. So 1, 0 doesn't. 1, 1 doesn't. 1, 2 actually does. 'Cause you could go, you go up onto it. So what I've not kept track of is okay. So what I've not kept track of is going back on yourself. Because we need to make sure we're not doing that. We can never go back to our previous cell. So that's another rule. As long as we follow that rule, I think we should be okay. So there's no like spaces or anything. We could just go around in a big wall. I don't think there are. Well, we will find out in any case. And maybe we'll have to keep track of slightly more cells. Anyway, okay, keep going. So this is actually going to, so really every cell has two inroads. We want to keep track of the ones that have three inroads. So it's really this. And then this one should be right. Yeah, okay. Fine. Now what is it? Neighbors. Okay. So neighbors is going to be actually of cursor. So to get the neighbors, we want to get all the cells around all the exits from that cell. And then we want to filter it in a couple ways. We want to say, so we've already filtered it based on the slope, so that's fine. And we need to not go back on ourselves. So in fact, we can probably contain this within, we can actually probably contain this within here. No, because we don't know the, oh, how irritating. Um, okay, so we've got the axis from the cell. Now we need to work out, we need to filter out we need to get all of the cursor. Yeah, so it's like I'm going to do a for loop. For exit in, nope. Right, so if the exit is off screen, we continue. If the exit is somewhere we've already visited, we continue. If the exit is back in the direction that we've just come from. Continue. If, and I think that's it actually. Otherwise, we create a new cursor with the new position, the previous position, and we need to work out if we're on an inroad. If we're on an inroad, then we need to create a new we do this. What is it again? Yeah, that's right. Okay, and then we add that there, right? So now let's check on the neighbors. Actually, may not do that. Um, okay, so we've now got the neighbors, allegedly. Could I check just one? Yeah, let's do it. This is going to be an empty set. Okay, now this should be a set consisting of okay, so we're on 7-4. We can go, no, wait, we actually want to be on 6-4. This would be 5-4. Yeah, okay. And now in this case, our possible neighbors should be 7-4, 6-4, and a frozen set consisting of nothing. Can't go down from there. Okay, if the exit is not in our current cells, no, wait. If the so this is the these are the exits, and we want to get that exit entries. So we want to get is the cell, if the cell is not in, oh my gosh, this is so confusing. Okay, so it's not off screen. Ugh, okay, right. That's good. Okay, now if instead we had this vector in the frozen set, then this set would be empty. Okay, I think that's good. Let's take this focus off. All right, that's the neighbors. Now let's move to the pathfinding. So slow today. I don't know why this is. Okay. This is going to be 1 on the x, 0 on the y. Then the end is going to be let me set this here. What is the end? X4, Y7. 0, 1, 2, 3, 4, 5, 6. Why is that so large? So many mistakes today. Okay, there we go. That's why. Okay. What line is this? Line 60. Oh yeah, I don't need that. Okay. Where is this? Oh yes, I've got to order. Yeah. Ugh. Uh, mm, 13. That's good. Okay, let's try it on. No, wait. I haven't actually done anything right. Okay. Yeah. Okay, that's good. That's definitely going to work as well. Okay, in which case we've got a calculate, and this is going to be every line, state, file name, files line, and then we're going to have visualize the state, and then we're going to count steps in the longest path. Hmm? That's not right. 90. I've gotten it wrong. Okay, let's take a look at where we've gotten it wrong. Hmm. Okay. try hard coding it and see if it gets through. That'll give us some more information. And this is 0, 1, 2, 3, 4, 5 by 0, 1, 2, 3, 5, 3. No, 3, 5. Okay. Now, if we do this, let's return a set of x. No, return a set of cursor where we're going to go right 4, 5, 3, 5, and our frozen set is going to then have to include this. Okay, so it can go along that route. It's just not, it doesn't believe that it's better, maybe. What does it do then? It goes off around there. It doesn't go, yeah, it doesn't go down that route. It goes around. Yeah, okay. So let's hard code that again and see if it can continue from there. Okay, so we're on, where are we on? We want to be 2 up, about 8 along, 10 along, 11 along. Okay. So vec 11.3. We then want to go down instead. So instead of going along, we want to go down by 1. Now, if we do that, we go down, along, along. Okay, and then we go, yeah, so we get now to here where we're not doing the right thing. So let's try hard coding that and see if it can get there. Looks like a lead day. That's a shame. Okay, we want to go like 20 down. Maybe like 15 down. Where are we now? Okay, and then recross. Yeah. Okay, so at 13, 13, we want to go right instead. Okay, and that gets us our 94. So my suspicion is that at these critical points, we are not putting the right values in. So let's look at this. Okay, so we've got 4, 5. We've got 3, 5, and we've got the inroads. Now, technically, this one is all right, isn't it? So we don't actually have more than one inroad there, I don't think. Yeah, so this one actually is okay. So okay, so that one's fine. Let's try it with the 11, 3. Hmm, we never go there. We never go there. We were cutting out the paths too soon. Yeah, okay. Okay, now we're good. It's a bit quiet there. Okay, so the trial's now 94. Now, what would the input be? That giant number. Let's try that out. Okay, that's part two, or part one. Let's take a look at part two. As you reach the trailhead, you realize the ground isn't as slippery as you expected. You have no problem climbing up the steep slopes. Now treat all slopes as if they were normal paths. You still want to make sure you have the most scenic hike possible, so continue to ensure you never step onto the same tile twice. What is the longest hike you can take? That doesn't seem so difficult. Every time I've said that, I've regretted it. Not every time, but a lot of times. Okay, rather than trying to guess this, I'm going to give myself a pause and I'm going to just go ahead and implement this the crude way. Okay. Getting an even shorter one now. I wonder why are they even getting the minimum one anyway? Should be getting the maximum one. 154. Yeah, that's so weird. So weird. Why did I get that? Why did minimum work on the last one, but not when I found the goal straight away? That's so weird. Okay, well, anyway, let's try with the input. It's taking a little while. We visualize this out so we can get a sense of what's going on. So you shouldn't do this, but I'm not actually going to use it. Very small. Hmm. So are we looping infinitely then? Is that what's going on here? Let's try that one, I guess. I don't know whether we're in some sort of loop or something, or no, too low. Okay, so we're missing some sort of path. Oh, we're going around in circles or something. Are we going around in circles? Or are we just trying all kinds of different paths? Let's try this out. So I should show you this. It's kind of good to watch. I don't know why it's so much slower this time. Okay, so one thing we can see is that there are definitely some like this there are definitely some like segmentation points, and they're relatively limited in number. So so we're probably going to be able to um treat these as yeah, I mean they're not yeah, they're they're not totally trivial, but you could definitely break this graph up into a number of smaller pieces. And I guess those are the entry points, right? Those are the inroad cells. The suspense is killing me. And then I suppose you could reuse portions of the graph, right? You would be having the cursor store that state is yeah, going to result in unnecessary recalculation. It's clearly found the exit. Found a number of ways to get to the exit now. Okay, so here's an idea. Let's pause it here. So, oh, no, I don't want that. Could we go back? So an idea is um, we essentially pre-process this with only the extracting only the junction cells, and then we treat um, yeah, we treat all of the ways to get between the junction cells um, as a new graph with yeah with cost of the negative of the distance between them. And then we've got a much simpler problem to solve, or a much less computationally intensive problem to solve. Okay, well, I'm going to take a break anyway, and I'll come back to this later after lunch. See you then. Okay, so in the middle of optimizing this, but I've just come up with a higher answer than I've had before, so I'm just going to put it. Oh, that's even better. Yeah, 59778. So let's see if that's it. Nope, still too low. Okay, let's keep optimizing then. May as well start recording again. So I've mostly just been optimizing so far and trying to, without shoehorning things too much, you can see I've distilled down the points that are relevant. Oh, we got another one. Well, this could be our last chance to get it in with bronze, so let's try that as well. I think it might complain now though. 6046. Nope. Oh, okay. Let's try it just before the timer elapses, and we can see whether we can scrape by with a bronze. It's just kind of worrying away at the moment on the more optimized version. I'm pretty sure I can make it even more optimized. Well, I'm certain I can. Obviously, there is an optimized solution. Oh, okay. 6086 is the newest. Should we give it any longer? Let's try it now. No, it's not that either. Okay, well, fine. Looks like it's going to be a double lead today. Yeah, so I'm making some decent progress though. Oh, 6106. Okay, it's even better. Okay, so yeah, where was I? I'm sort of working on um all right, good exits. Let's go with cursor cost. Yeah, there we go. Okay. Okay, so 6106 is the highest so far. Okay, let's try running this. Oh, it's really sticking there, huh? Okay. Okay, that's considerably faster. You're not going to get a wrong answer here. I might do anyway. Okay, 6106 is wrong. Why 188? I'm going to keep muddling away at this and then I'll see you later. Hello. So, I've discovered this is notorious problem, longest path problem, allegedly, or at least that's how it seems to me. So we have a bit of a challenge on our hands. Um, I have got some sort of answer, another answer. It's significantly higher than previously. Um, so, like, basically what I've done is I've used my initial part part two to generate a list of edges between the junction points and the cost to access them, which happens to be all the same just because of the way I'm doing it. Um, I probably could have done this hours ago, but I didn't. But I'm doing it now. So if I copy this and I show you it in GraphViz, you will see what it looks like as well. Okay. Oh, it's actually too big to look at in GraphViz. Let me take a bit out. Okay, so this is not all of it. I've just arbitrarily cut out some of it. Um, so yeah, let me show you this. So it looks kind of like this, bit messy. If this is wrong, obviously, then all of my work is for naught. And I have very little way of verifying it. So yeah. Anyway, so I'm working on that idea, and then I wrote another program to do A star again on um, on the data on the edges generated by my original part two, rather than kind of shoehorn it in. This has generated the following number, 12 80. So we should put that in and see if it is right. If it is, I'll be very happy. What is it? What was it? 12, 8, 10. All right, 12, 8, 10. Nope, still not right. Hmm. Okay, well, back to the drawing board, I guess. So periodically, I'll copy these out again and just check if I found any more edges. Have I found any more? No, they're the same. So, like I could go through and make sure I've got all of the all of the points. I mean, that would be good. Be a good idea. Okay, I'll do that. I'll see you later. Oh, where's my audio? Here we are. This is E.
Hi.
Would you like to say any words?
Um, Hello. I think Advent Code has a lot of bits.
Yeah, true.
Yeah. And I think it's impressive.
He is here as my partner, as moral support for this number, which is one higher than the last number, which it could have been. Basically, what I've done is uh, I've somewhat gutted this code to generate a list of the nodes, which we can see here.
Cool patterns.
Yeah, good patterns. Um, and oh no, see, it's done that. I hate it when it does that. Okay. All right, well, fine. We'll just zoom it out. Terrible. All right, here it is. Yes. And now we can treat these as our sort of graph to be optimized. And that still takes a while. I'm pretty sure there's a faster way, but it's kind of fast. I mean, if I run it again, it doesn't finish, but it does get us this answer reasonably quickly. And then it takes a while to just complete. So because given it finished, in theory, it should be right. So if it's not, then E's going to be very sad.
Oh, the suspense is huge.
Okay, are
Okay.
you ready?
Yes, I'm ready. Let's go, Kay.
It's the right answer.
Yay!
Yes, it is.
Yay!
Yeah.
Well done. How do you feel?
Good. Relieved. That was a difficult day.
Was it? Well,
Yeah.
you did say you'd been working on it since like 12.
Yeah.
So
Yeah, don't
sorry.
tell them
Well,
that.
they don't know what time it is now.
It's only been exactly as long as the video is. Yeah, okay, that's good. I think I had the right idea fairly early on in part two, but I failed on the execution again. But I guess I was sort of continually underestimating how long it would take, which I probably shouldn't have done. Anyway, that's it for day 23. Hopefully the hardest day, or hardest day for me. See you tomorrow.
Bye.